So thank you, Diego, again for the introduction, and thank you for coming. Today I'm going to talk about this Hajlasz capacity density condition, which is a condition that was introduced by us in our last work. And I'm also going to state that the main result in our work is that it is actually self-improving, both in both parameters. It has two parameters, beta and p. I'm going to explain it in a bit. And we are going to show that it is self-improving. And this is joint work with Antti Hajlasz from Finland, from University of Basque. So since I don't know the background of the audience here, so I'm going to introduce what usually is a capacity. There are many ways of defining capacities in many situations, but so the most simple one is to define the capacity of a closed set in Rn. So the variational capacity, and it depends on some parameter p of the set inside of another open set, is just this infimum here when you have taken, okay, so this f is a u, right? So you have taken a function that is 1 on the set and 0 outside of the domain in which you want to calculate the capacity, and you take the infimum over all derivatives overall the LP norm of the derivative of your function. And the idea is to use to change here the derivative you're going to use, and we are going to change that to a fractional derivative in a non-local derivative in terms of Hajlasz gradients, and we are also going to work in metric spaces. So let me just make a small comment on the history of this problem. So as I said before, we are going to use not the traditional derivative, but we are going to use fractional derivatives which are non-local. And the first somehow condition that appeared in terms of these types of derivatives that was involving capacity density conditions was by Lewis in '88, where he proved, well, he gave in Rn a condition involving Riesz capacities, so capacities using Riesz potentials in Rn, and he showed that these these capacities are self-improving, both in beta, which is the derivative, the order of the Riesz derivative, the Riesz potential, and p, which is the parameter that says the size of the integration. And later, these kind of results were somehow generalized to other metric spaces by Björn McManus and Shanmugalingam in 2001, and they used the derivative they used in these metric spaces is the upper gradients. So upper gradients is a very different object from Riesz capacity, from Riesz gradients or Riesz derivatives, because they are just it's not an easy thing, right? But they are a local object. So the value of the upper gradient doesn't depend on more than just a neighborhood of the points. And then this this result was somehow revisited by Tuominen, Lerbach, and Hajlasz in 2017, where they somehow unified these capacity density conditions with some Hard inequalities, and they proved similar result using hard inequalities in a local sense. And once you have these hard inequalities that they are somehow similar to Poincare inequalities, you can use the self-improvement technique that was invented by Keith and Song in 2008. And with these self-improvement techniques, you can somehow prove these estimates, these self-improving properties of these capacity density conditions. And moreover, we are going to somehow follow the more recent approach by Kinnunen, Lerbach, Hajlasz, and Song in 2019, when they use some kind of maximal operators in order to get these Poincare inequalities and use their self-improving to get some capacity density condition and their self-improving. So we are going to work in geometric spaces. So we are going to have a metric space X that has a distance d and a doubling measure, Borel measure mu. That is, a doubling measure is just a measure such that the ball of radius 2b, of radius twice the, so if you have a ball and you have the radius, the ball with twice the radius and the same center, sorry, so the measure of the bigger ball is controlled by the measure of the smaller ball. And we are also going to assume that X is a geodesic space. That is, so if you have any 2 points, X and Y in your space, you can join them by a geodesic curve, such that the distance from X to Y will be the length of the curve. So this assumption, this geodesic assumption, is a technicality because we need a few properties that arise from this geodesity. In particular, we are going to use very often that the measure in a geodesic space is reverse doubling. That is, you do not only control the measure of a bigger ball by the measure of the smaller ball, but you can also say that the smaller ball is always, sorry, this inequality is in the wrong direction. It should be greater or equal than this measure of the bigger ball. And another good thing about geodesic spaces that is not true for a general measure space is that if you restrict your measure to just a ball, right? So you take the sigma algebra restricted to the ball. In that ball, you have that the measure is still doubling, and this is not true for all measure spaces. So now let me introduce what gradients we're going to use, which are the Hajlasz gradients. This is a way somehow of defining a fractional derivative in a metric space that is quite intuitive, and it's quite natural. It appears quite naturally. It doesn't involve quite a heavy machinery for the definition. So these Hajlasz gradients are defined as so if you have a function defined in a metric space, a Hajlasz gradient of your function will be a function g satisfying this inequality here. And this inequality somehow plays the role of the mean value theorem in the classical derivative scenario, right? So the distance between the images of x and y, so the distance between ux and uy has to be controlled by the distance from x to y to the power beta. Beta will be some number between 0 and 1 and will be somehow the order of the derivative that we are taking. And this distance times the sum of the function of the gradient at x and at y. And this has to hold for all x and y outside of some exceptional set that has measures, right? And we are going to write that, we are going to say that in this case, G is a Hajlasz gradient of order beta of U. And the basic properties of the calculus of gradients are also applied here, right? So we have somehow the linearity. So the multiplying by constants is allowed if you maintain here the absolute value of the constant. And also summing of the gradient of the sum is the sum of the gradient as usual with usual derivatives and other derivatives. And some kind of chain rule is also true, but the non-locality here is reflected in that the derivative of this f should be the whole derivative on the whole space, right? So if f is Lipschitz in the whole space with constant kappa, then this whole kappa will appear here and while computing the derivative. So these gradients are non-local in the sense that so if you have a function that is constant on some set, you cannot assume on an open set, you cannot get that the gradient will be 0 on your set, but there is somehow a property that allows you to compute the derivative when you know the value of the derivative of a function, for example, here v. If two functions agree on some set and one of the function is beta Hölder continuous in the whole space, then you can compute the derivative here, depending on if you are on your set or outside of your set, and this relation holds. And you need to know the value at every point of the space. And this somehow is also reflected in with the product of the derivatives. So there is also a Leibniz type rule while working with these gradients. But what I think is the most important thing in our context is that this gradient always satisfy Poincare inequalities. That is, if you have a metric measure space and any p, this inequality here holds for all gradients of your function. So this controls somehow the oscillation of your function on a ball by the size of the derivative in the same ball. And this holds somehow for free. And this is not true for other gradients. For example, in the Euclidean space, there exist some measures that are A infinity, for which there exists some exponents P, and this inequality doesn't hold for those exponents, right? So, so somehow we get that these Hajlasz gradients are somehow natural in this sense, right? And also we can use standard self-improving techniques in order to get that we can have the exponent here, the P here, we can make it smaller. So there exists some Q smaller than P such that this inequality still holds, and this will be the beta P Q Poincare inequality. Of course, this Q will depend on both on P and on beta, but also on the geometry of the space, but will not depend on U. Okay, so now that we have the main character here, which is the gradient, we can define a capacity condition. So if we have a set F inside of another set omega open, then we define the Hajlasz capacity of parameters beta and P as this number here. So it will be the infimum over all functions U and all gradients of those functions G, in a way that the function U is greater than 1 in the set and is 0 outside of omega. And we are going to require that, so we are going to integrate in the whole space X. This is important. We have to integrate in the whole space X because derivatives here are non-local. And we are going to integrate the P power of the derivative, of the gradient, sorry. And also we can assume that U is exactly 1 on F and it's always between 0 and 1. This is allowed. So now that we have the Hajlasz capacity, we can define a capacity density condition. So by a capacity density condition, we mean that a set satisfies the capacity density condition if its capacity is dense. That is, if you intersect your set with a small ball that is centered at your set E, and you compute the capacity of that truncated set inside of a bigger ball of twice the radius, you need that this capacity has to be somehow greater than the measure of the ball, with some correction here depending on P. Right? You can also define somehow equivalently this a condition here that is equivalent to this one with capacities in both sides. But in our preprint we have it in this as this condition here. And this has to happen for all R that are bounded by the diameter of E in this way, because if E is bounded and you don't impose this condition here, then there is no way that a bounded set would satisfy this capacity density condition. And a good thing about this capacity density condition is if you think of your set as the boundary of an open set, then you will have a boundary Poincare inequality if your set satisfies a capacity density condition. That is, a set satisfying a capacity density condition is somehow enough so that if a function is 0 on that set, you get a boundary Poincare inequality. So you control the size of U by the size of its gradient. If U is bounded, if U is 0 on your set E. And as I said, the main result here is that this capacity density condition is self-improving. So we need to use a characterization in order to get that this is self-improving. So the characterization we are going to give is in terms of this upper Ashwat codimension of the set. So we are going to say that the codimension of the set, the upper Ashwat codimension of the set E, is the number Q such that this inequality here holds, right? So it's the infimum of all Q's such that this inequality here holds. This inequality here says that, okay, so take your set E and take an open neighborhood of your set E with a small radius R. So this purple stuff here. And then take at the same point, at a point here, a ball of radius R, big R. And then you have to check that the part of the neighborhood of the set that is inside of this BR in measure is somehow bigger than the ratio between two R's, these two R's, the R, small r and big R, in the correct power. And you need to impose here this these conditions on the radius. So if you think about it in the Euclidean space with regular sets, this Aswad codimension will be equal to the Hausdorff codimension, right? If your set is regular enough. This is another way of defining the codimensions here in measured spaces. So the main characterization here and the main result here is that if you have a set E that is in a geodesic space and a metric space that is doubling, then your set E satisfies a Hajlasz capacity density condition with parameters beta and P if and only if its Aswad codimension, this upper Aswad codimension, sorry, is strictly smaller than the product of beta times P. So now, since the codimension is actually a number, you always will have some room here of beta and P, and you can make them somehow smaller, right? So you can always find some beta prime that is smaller and some P prime that is smaller, such that their product are still bigger than the codimension. So your set E will actually satisfy a beta prime P prime capacity density condition with some beta prime and P prime smaller than your original beta and P. And the way of proving this is one direction is somehow easy. I'm not going to get into details because there is not much time, but to see that the codimension bound implies the capacity density condition is somehow easy, you just need to tweak a little bit of this expression and use Poincare inequalities, and it is somehow easy to get it, but it is not easy to get the other one. So it is actually easy to see that the capacity density condition implies a non-strict bound on the codimension, and this is just choosing the right test function and checking that it all goes smoothly. But if you want to have the strict inequality, that's when it's a bit harder. So the proof goes in 3 steps. The first step is some localization argument in which we make the set smaller, but not so small that we lose the boundary Poincare inequality. And we borrow this technique from this article by Juhaler, Bakeli, Tuominen, and Antti Vahkangas in a few years ago. Then we are going to use the Keystone estimates for Poincare inequalities. And we are going to use also maximal Poincare inequalities. And we are going to use some maximal operators that we define that are similar to the maximal operators that were used in this work by Kinnan, Lerbach, Vahkangas, and Thong in 2019. And then we are going to use Keystone estimates similar estimates to the Keystone ones that allow us to self-improve those maximal Poincare inequalities. And finally, we join them together with some local hard inequalities using some ideas and improve, in this context, that are from this is the same work here by Lerbach, Tuominen, and Vahkangas. These both works are the same. So with this, we actually can prove the self-improvement of the capacity density condition, because using the characterization between the codimension and the capacity density condition, it is very easy to prove that if your set E satisfies a beta P capacity density condition, then it also satisfies a gamma Q capacity density condition with gamma smaller than beta and Q smaller than P. And as I said before, this is just a matter of continuity here of the real numbers, right? Because if you have that the codimension is smaller than beta and P, it will also be smaller than some smaller number that can be written as this. So then the capacity density condition will hold also. And this is all I wanted to talk about. So thank you very much for paying attention and listening.